I hope you will join me in a bit of a conversation about some of the themes that have been thrown up by the readings. Before I throw it open to you guys, though, I just want to ask a couple of questions. First of all, with regards to the stories, it's in particular yours. So it's very sort of tied to a particular time, and I wondered why you chose that setting. It's a very particular thing to write about, and I was just wondering what your thought processes were.
We were having this conversation earlier, weren't we, about how we decided where we were going to set our stories. And for me personally, it just seemed, partly it was very timely that obviously next year is a big year in sort of commemorating World War One, but also it seemed like a really important and pertinent time to set it in terms of what was happening in the worlds of physics. We were having conversations, weren't we, about physics is actually quite, all the science is quite new. A lot of the discoveries have come quite recently, and Laplace's demon sits just sort of before the discovery of quantum mechanics, which sort of blows it all out of the water, really. So I wanted to set it at a time when that was still quite a frightening and real possibility that everything was determined and there was no free will, and that's why this period seemed so relevant. And also the whole machine of war, where you have all these individual people, soldiers brought together to become this massive body. It kind of had echoes of that idea that all these separate little particles are part of something much, much bigger that is being controlled elsewhere. They don't have a free will over what they were doing in the trenches and their responsibilities, and that it just seemed to feed into the Laplace's demon so beautifully. I couldn't really not have that setting. Yeah. It's
also a setting in which very different types of people were thrown together and brought into contact with, so all these kind of strange sort of dialogues can come into play. And likewise, Marie, you, not so much time but place, you chose a particular place and a set of characters. Why those?
I spent some time in New England earlier this year, and maple syrup making is a big business over there. So I just became quite interested in that process. I mean, obviously, professional production of it, they use huge machinery and things, but people do make it by themselves, and it's a very laborious kind of process. And I just started to imagine an older person kind of trying to make their own maple syrup, but really struggling with it, and that kind of fed into this sort of entropy question, really. So it's really just being there and spending some time there, which was why I decided to set it there. I'm sure if I hadn't have done, I might have set it somewhere else, and it would have been about something other than maple syrup. But that was the main reason, really.
My one science question, which will cover everything, I'll hand it over to you guys, is, Rob, you say they both fell apart.
Yeah. the resolution to each of them. Well, Laplace's demon's easy. There are actually loads of resolutions to this, actually one involving entropy, thermodynamics, but the most obvious, simplest one is quantum mechanics. In the quantum mechanics, we can't know the position and the speed of a particle to infinite precision. If we measure one, the other one gets really big, and vice versa. So simply the initial conditions, the speeds and positions at one instant, we can never know in a quantum universe. So that's easy.
So you're saying that, but before that, entropy also kills.
Well, yeah. So
one demon kills the other demon.
Well, not kills it.
Or rather, entropy, the thing that demon is trying to fight against, the subject.
Yeah, they have an interplay with each other, because what the second demon gives you is an arrow of time. So suddenly your equations for the universe aren't reversible anymore, which is a prerequisite for Laplace's demon. So it actually has something to say about the first demon, but in quite a subtle way, I think.
And Maxwell's demon?
Maxwell's demon, well, again, that's fairly easy. That you have to imagine what this demon would actually do. And so you have to sit there with a pen and paper and understand, as a molecule comes towards him, does he open his little door or not? And this act of measuring would increase the entropy of the system. So the entropy of the gases might go down in isolation, but the system of the demon and the gases as a whole, the entropy would overall increase.
Is it the measuring, or is it the sliding of the door backwards and forwards?
Both.
Okay.
Both would generate heat, which is disorder, which would be entropy.
So done.
So yeah,
Finished.
so done. Yeah, there are more modern interpretations to do with computation. So that say you have Laplace's demon, quantum mechanics is the easy way to explain it. The harder way is our computational physics friends only a couple of years ago made a proof using number theory that it would be an impossible calculation to make in our universe, which is a different way, a different statement than quantum mechanics.
Because there used to be the philosopher Leibniz used to say that he used to have this theory of monadology, of monads, and which feeds into this idea of every particle can understand every other particle. It's a reflection that contains some property of the other particle. So you just need to. So you don't need to stop, take a picture of a moment in time. You can actually just look at one particle, and in there's enough information about everything else. And he had this theory of best of all possible worlds. He said that we live in the best of all possible worlds, and the only person that can do the maths to prove that this is a deductive, logical necessity was God. And so you get this idea that we are a logical result of the best of all possible worlds, which was then parodied by Voltaire and Candide, which is a big joke about us living in the best of all, quotes, best of all possible worlds.
Gives us the word optimist.
From Coles. Right. I did not know. So over to you guys. Does anybody have any questions? We've covered everything.
There will be a test on the 30th on the way out.
There already has been.
You already kind of linked the two, right? But does the uncertainty principle violate the second law of thermodynamics?
Well, no is the statement, because both are meta theory, so both must be obeyed by any sensible theory of our universe. So the second law of thermodynamics is a statement about the overall increase in entropy of a system. That's not saying anything about the individual quantum behaviour of the particles that make up that system. It's more the meta theory. Whereas the Heisenberg relation has all to do with the behaviour of subatomic particles, things at the quantum scale, so they're very, very small. So both need to be. If I write down a theory tomorrow and I show it to you and it violates one of these two things, you should look very sternly at me, because they both have to be respected.
What I think is interesting is, well, it's all interesting actually, but particularly what I'm picking onto was this whole thing about what time is and how we deal with it. And in fiction, we actually deal with time in a way that challenges the whole idea of entropy. That actually we can only move forward. We can think back. We tell stories about what happened in the past. We can postulate what's going to happen in the future. And of course, we don't know. And sometimes it turns out that what we postulated is absolutely spot on, and sometimes it isn't. But we have this amazing ability through telling stories to be able to mess with time. And I think that for me is fascinating how we can do that.
I think you're right, and there's precedent for it in literature. Kurt Vonnegut's Slaughterhouse 5, he has these aliens, I think they're called something like Telemachians, or they have a very long, strange name, and they see time as just like a mountain range. They see it as a single picture, not as we see it. They sort of stand back, but it is a Laplacian point of view, that everything is there, and they just move in and out, and so does the narrator of Slaughterhouse 5. Just, I'll go and have a look at that bit over there, and I'll go and have a look at that bit over there. And it is a literary conceit. It is a very literary device, as you say, this idea of non-linear, non-chronological stories, which I think your story brought out fantastically.
I think here, what's more important is the storytelling and not the rigorous adherence to the physical principles. I think we all should be happy to throw away physics if it tells a good story.
Which I think yours does, the idea of this little demon and the result, and the things which I know that happen later in the story, in Marie's story, which you'll find out.
Don't spoil it.
Yeah.
I know we didn't get the beginning. I take it there was more afterwards as well.
Yes, yeah.
So we'll have to get the anthology.
Yeah, I'm sorry, it was a bit of a... I wanted to sort of work with the sciencey bit, because I think you know, it's nice to have that kind of comparison. So yeah, I picked the bit in the middle, which is the key, it's the science moment of the story.
How did you go about this? Did you go and talk to some physicists?
Yeah, I should probably explain. I rushed through my intro. What we do with these projects is the scientists, I speak to a bunch of scientists around a certain thing, and they suggest a particular topic. So in this case, I spoke to a whole load of physicists, and they nominated their favourite thought experiments, because there's loads of thought experiments in physics. And then the writers came along and picked theirs. And Claire's also part of this project, and she's chosen a different one. It just so happened that the first two writers in this longer project, which is going to take several months, both chose a demon. Why did you choose these particular demons?
Well, we were having this conversation as well. Do you want to?
This particular one appealed to me the most. I mean, they were all very, very interesting, fascinating, really. But I don't really have another explanation other than that. And the more, because before I sort of chose one, I researched a little bit about each of them, and this just one really appealed to me. I mean, Laplace's demon as well, I found very interesting.
I think for me, I looked at the list at these fantastic options of areas to write about, and a lot of them I just felt like I'd taken my brain out and turned it inside out, because I couldn't understand even that it's just so different to anything I'd ever sort of done before. So I had another look through and sort of ticked the ones that I thought I could cope with. And one of them was Laplace, and I think for me the thing that really took my interest was this idea of determinism and free will, and I find that whole concept fascinating. I think that was my springboard to choosing that. But I think I started, when you're writing, you sort of start with all your ideas, and then you throw that list away and you think of new ones, so you're finding something, a fresh angle. I think my first idea was I was going to write about a robot church. So this idea of like these automated robots wanting to be free. That went.
Stanislav Lem, I think, has actually done it.
Yeah,
that's
true. Yeah, that was my sort of take on picking it. Yeah, and then talking to Rob.
But part of it is the conversation that we have is so important. Just a free-form chat, over a coffee or over Skype. I think it's a lot of fun. I think you have to do it with no agenda and just discuss the physics and let the ideas naturally emerge.
And we're sort of free to ask
anything,
and you can just point in the right direction.
Yeah, I think at one point in our conversation, we were like, if it's all predetermined, did we choose to be here having this coffee? Did I choose this coffee? Yeah, it gets scary.
That was a fun coffee on Oxford Road in Manchester, wasn't it?
There is a theory that we think free will is just this delusion. Every time we carry out an act, a millisecond afterwards, the brain convinces itself that it wanted to do that act. And it sort of instantly reimagines us making the decision and willfully, saying I could do this, I could do that, but I actually chose that.
It's rather troubling, isn't it?
Yeah. Another troubling aspect of this, if we're going there, is you talk about uncertainty and entropy being two meta theories. They sit on top of all the other theories, and if that's the case, so if you look at entropy, one of the consequences of that, obviously, is the heat death of the universe, which Brian Cox made a good show about, and this idea of that everything just gets more, heat disperses and things get more and more disordered, and it's just more and more like a big sand dune, and energy is just lost until eventually it gets to the point where the energy is so far apart, any bit of space is effectively dead and there's nothing there. There is another theory, I think it's Lee Smolin's, that says that in this space, new universes start. So I'm just my last question here will be, do you agree with that, or where do you think it all comes from?
This is way beyond my expertise, actually. I'm not a cosmologist, and I don't understand what these quality theories come up with, because some of them are just crazy. I like to think there wasn't a heat death of the universe, but if that
won't be.
Well, I like to think that as a person.
There'll be a big crunch.
I don't know. I think physics is very well, as a theorist, I'm very cautious about what I would predict about what physics can say. It's very crap in that sense, that it's very restrictive. I think we don't know what's going to happen to the universe. We don't really understand what happened before the Big Bang, although there are some good theories about it. So you find physicists saying they have this idea what's going to happen now. They have very little idea compared to the rest of us, I think. We don't know. That's the answer to most physics questions. We don't know the answer.
But you're here to tell us.
I don't know. None of us.
No, we're here to tell him through stories.
Yes,
Exactly.
But isn't there an interesting thing there that there's that space for creativity there, isn't there?
Yeah.
That space for
Within the confines of what we call scientific imagination, so you obey the existing theories of our universe, which are theories just for our universe. So you try to make statements what happens beyond our space-time, which we all sit in, you can't do it anymore. This is my trouble with theories like Hawking talks about what happened pre-Big Bang, where for me our theory is built upon on this big space-time. It goes to a single point. So our theory, so we can't extrapolate to negative time beyond the Big Bang, as far as I'm concerned. But people try, because it sounds sexy and cool to be in the newspaper. But for me, you don't know what's going to happen. It's a point of zero information. So how can one extrapolate beyond that to negative time before the Big Bang? That's my personal view.
So you're an Occam's razor kind of guy?
Well, I'm a pragmatist, in the sense that physics is very restrictive. We assume everything's made of particles and everything. Our universe is quantum and obeys Einstein's relativity. That could be a load of rubbish, but it seems to work very well. So you find these people going all in all directions. I think they get a little overexcited sometimes.
Guys, a question sort of following on from that, which is, so far our understanding of the universe is constantly revised through history as sort of new breakthroughs in physics happen. Which of the sort of consensual laws of physics do you think would be the first one to go? Which are you most suspicious of at the moment?
The three big assumptions that everything's made of particles, our universe is quantum, and it obeys Einstein's relativity, but we're having great trouble. So that all works very well. The Large Hadron Collider, we do experiments, we understand how things have mass now through the Higgs boson, and that seems to be working extremely well. It's a very highly tested theory, but we can't incorporate gravity into this theory. We look at galaxies very far away, and they're not attracting each other according to gravity, they're actually repelling. And the further apart they are, the faster they repel. This is we call it dark energy, because I have no idea what it means. So something's going wrong. So I think, for example, an attempt to chuck away the particle concept is the string theory, where everything is not little particles, but little vibrating strings in 11 dimensions. That seems to be coming out to favour. Quantum mechanics has passed all its tests, so has relativity. So who knows what's going to happen? This is why we have these new big colliders to probe the fundamental levels of nature, to see what's really there, hoping at some point it's all going to go wrong with our theories, and then we'll have the next generation of theories. So the modern view is it's an effective theory. It works on a certain energy range, and we have to have a different theory for the next energy range. And one day, fingers crossed, we'll have some kind of fundamental theory if we're really good at doing our jobs, which we're not at yet. Does that make sense?
Yeah. I'll watch the video later.
Hasn't that always been the case, though, over time, that someone comes up with a theory which works within the confines of the current levels of understanding, and then that's refuted, and then...
Well, take example here, Laplace's demon. The classical laws that talk about are Newton's laws of motion that work when the speeds of things are really small. We found out at the start of the last century that when things get really fast, there's actually a different kind of mechanics you need to use called special relativity that only applies when velocity's speeds are very big. If you take the classical limit of this Einstein's theory, you recover the classical Newtonian theory. So of course Newton thought this is a very reasonable theory to have, because it approximates a bigger theory in the right limit at low velocities. This is one thing all these cranks always don't appreciate. You get letters like, I've got a new theory of the universe. If your new theory is so good, why does the current one work so well? Any new theory has to explain that. Why does quantum mechanics work so well? Why does relativity work so well? Because it does. So it may not be the final answer, but any new theory has to tell us why this old theory worked so well.
Any other questions?
You've got a letter from a crank in before.
In Scotland though, because they have no maths in them. So maths is quite a useful tool for doing quantitative analysis. You can always spot these people. Then he didn't do very well at GCSE maths and ended up being cranks.
But they write to you personally?
Well, yeah, Brian gets the most, obviously. In fact, by order of magnitude, he gets the most. His pigeonhole at work, he has all the pigeonholes at work, our coffee area, and has some things, some student work, a couple of letters. Brian's overflowing every day, letters from fans and from cranks and all this kind of stuff. So we send them to his agent. A little bit. So he's the only academic whose post gets sent to his agent. So he gets most of them. We all get them, and put them in the coffee area and discuss them. We can spot them. No.
You really discuss them?
No, not in a serious way. We can spot them because they're not, there's always a danger of saying, we're just rejecting those, not inside our scientific paradigm, but we have principles we adhere to, so testing our theory against nature, make quantitative predictions that these theories often are not able to make. So I think testing a theory against nature is pretty important, but that's what we do. So any other theory that comes along. If someone tomorrow, a physicist, if a theory came along tomorrow that was totally new, that agreed with nature, we'd all believe in it straight away. That's the difference between, say, a physicist and a person who's a crank.
But one way the crank can get into the conversation and make a point is perhaps through a thought experiment, without doing the maths.
Oh, for sure. Yeah, okay, fair enough. Yeah. That's true. If they pointed something out that was arguably true. But I think the theories nowadays are very complicated and very mathematical. So it's much harder nowadays than it was to do this maybe 200 years ago.
But then, sometimes they're quite simple. I was thinking about the Casimir effect. Does that violate second law of thermodynamics?
No.
Can you explain that?
Yeah.
So that's quite a simple idea that when we look at quantum mechanically, the vacuum, we find there's lots of particles popping in and out of existence in relation to the uncertainty principle. If you get two plates and they're close enough together that some particles can't pop into existence, you have a lower energy state there, and the plates will tend to push together. And this has been proved.
This is correct. Yes.
So in theory, it sounds like you could extract some energy from the fact that if you get two plates.
Yeah, you could, but the universe as a whole would obey these grand principles, I think. Maybe have a local violation, maybe, but overall you would still obey them. Certainly there's no evidence so far that the second law is violated anywhere.
Maybe pushing them together so close requires energy in the first place.
It's our next story right here.
Anyway, definitely I need to thank the Institute of Physics, which has funded the first handful of stories in this project, which will hopefully, which will turn into a book at some point next year, and also the Arts Council. But finally, most importantly, please can you join me in thanking tonight's speakers, Dr. Rob Appleby, Mary Louise Cookson, and Sarah Schofield.